Hello, this is our unit on chemical equilibrium. This is lesson 7.1, 7.1b, tutorial number 2. Okay, we're still talking about the equilibrium constant. Here we have an equation. These are all gases. We have A, the little letters are our coefficients, big letters are our molecules. And because pressure is proportional to concentration for gases in a closed system, we can also write our equilibrium expression using pressures instead of concentrations. When we write it with concentrations, and you don't always see this little c down here, by the way, we use molarities to the power. If this was A, and this would be B to the B. Actually, this would be for, let's just do it for the same type of reaction. So we have reactants on the bottom, products on the top, and they're to the power that is their coefficient. And this, writing something this way is also called, you may see it referred to as the law of mass action. But this is how we write our equilibrium constant expressions. That's what this whole thing is. And because pressure is proportional to concentration, directly proportional, if we have all gases, we can use pressure. It doesn't matter what units as long as they're all the same. So as long as these are all atmospheres, that would be fine. They're all going to, if these are all, or else they could all be millimeters of mercury, they just have to all be the same. You may have noticed, you may not, there are no units for the equilibrium constant. It is unitless. So I'm going to discuss this, although we probably won't work many problems with this. You can convert between K equilibrium constant written in concentrations to the equilibrium constant written in pressures, because we know that pressure times volume equals number of moles times R times temperature in Kelvin. We can rearrange that to find what pressure equals, moles over volume times RT. And our number of moles is going to be our coefficients, by the way. So if we were to plug that into this expression for Kp that we said 2 slides ago, we could come up with an equation to translate the equilibrium constant for concentration to the equilibrium constant for pressure, if we wanted to. And this power, this change in number of moles, is equal to the moles of gaseous product to the moles of gaseous reactant. I can't really think of an instance where you would want to change, or need, I mean, I'm sure there are times when you would need to change the equilibrium constant from concentration to pressure, but I don't think we will need to do this. This is not on the AP exam, so, I mean, not on your equation sheet, so we're not going to work any problems working with this. But just know that if you can, if you're given the equilibrium constant in concentrations and you know your number of moles of your gaseous products and reactants, you could figure out your equilibrium constant for pressure, and you, I guess, would do that if you weren't given the actual pressures. Okay, moving on. It's very important to realize that equilibrium can be reached from either direction. So what this means is if we start with only N2O4, for example, in this reaction, if we only had N2O4, we would still reach a situation where we had an equilibrium between N2O4 and NO2. The rate of the forward reaction would be equal to the rate of the reverse, and rates are different this is at a specific temperature, whatever that temperature is. And so you'd have a certain concentration of this and a certain concentration of that at equilibrium. They would seem to be not changing. And here is data that supports that. In the first 2 experiments, we start with no N2O4. So we have none of this. We only have the NO2. But at equilibrium, we have a concentration of both. And the equilibrium constant is 0.211. In the third experiment, what happened? Oh, actually, that was the same. In the first 3, we had none. In the fourth experiment, we start with just N2O4, so we would just have this, different color, and we had none of this in the fourth one. But at equilibrium, we have a concentration of both, and the equilibrium constant is about the same within, experimental error. So your Kc is the same, equilibrium constant is the same, because it equals your concentration of your product, NO2 to the order that it is, over your N2O4 to the first power. And that ratio is going to be the same once you reach equilibrium, no matter what you start with. If you start with just products or just reactants. Here is another picture of the same concept. So in experiment 3 here, we started with, well, you can see it right here, 0.04 of NO2 and no N2O4, and the concentration of NO2 decreased in experiment 3 as N2O4 increased. In experiment 4, you started with no NO2, but over time it increased. And at the end, at equilibrium, the concentration was the same, whether you started with a lot or zero. And that's because at equilibrium, at a certain temperature, your concentrations of your products or reactants will be the same. Or really, I should say, would be in the same ratio. This is a third way of looking at the same concept. Here we're working with the Born-Haber process that makes ammonia from nitrogen and hydrogen. This is an extremely important discovery in World War I that by chain, which we will talk about when we're together again. So in this first picture, we started with a lot of H2 and a little bit of N2 and no NH3. But we reach the same proportions of the three substances, the same ratio, H2 to NH3 to N2, as if we were to start with a lot of NH3, the product, and none of the reactants. Even if we start with none of the reactants and a lot of the products, after equilibrium we have the same ratio of H2 to NH3 to N2 that we would if we started with all reactants and no products. At equilibrium, the ratios of products to reactant is the same. And that is why we write our equilibrium constant expression as a ratio of the products, in this case it would be NH3 to the second order, over the reactants to the second, and H2 to the third. So, moving on again, we're going to think about what does the value of K mean, or we've been calling it Kc or Kp. So if K is much, much greater than 1, that means the reaction at equilibrium is product favored. So at equilibrium you will have mostly products. Because in order to have K be much, much greater than 1, our concentrations of our products in this ratio must be much greater than our concentration of our reactants. On the flip side, if K is much less than 1, that means the reaction is reactant favored. So at equilibrium, and all this is at a certain temperature, you change the temperature and equilibrium changes, the equilibrium point changes. But having said that, if K is much less than 1, then reactants will predominate at equilibrium. Because let's look at our expression. K equals, we'll just write K, we won't put a C here. So if K is much less than 1, that means that the denominator has to be much greater than the numerator. If the denominator is much greater, that means the concentration of our reactants is much greater than the concentration of our products. So if K is less than 1, at equilibrium, you have many more reactants than products. The reaction, we say, it hasn't really moved to the right in that case. So unfortunately you don't have this picture in your notes, but we are going to practice interpreting the magnitude of an equilibrium constant. Move this up here. Okay, so the following diagrams represent three systems, all at equilibrium, all in the same size containers. So without doing any calculations, we're going to rank the systems in order of increasing equilibrium constants. So that's just for A. So let's look. In A, our products are blue. So we have 1, 2, 3, 4, 5, 6. Oops. 6 blue. over 1, 2, 3, 4 reds. That's our K. For this one, it is, our products are yellow, so we have 1 over 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. And for this one, our products are red, 1, 2, 3, 4, 5, 6, 7, 8. 8 over 1, 2, 2 reactants, 2. So which fraction is larger? This one. So the equilibrium constant for letter 3 is the greatest. Then for B, if the volume of the containers is 1 liter and each sphere represents 0.1 mole, calculate Kc for each system. All right, that's basically so remember, molarity equals moles per liter, and our liter here is 1. So whatever moles we have is going to be over 1, so we can just write that, and our symbol for molarity is brackets. So over here, we're going to have 0.6 molarity, because we have 0.6, and this is 0.4, so Kc would be equal to, so the value of this K, oopsies, is 1.5. For situation number 2, we have 0.1 molar over 0.9. And these are all to the first power because the coefficients are 1 in each of them. So 0.1 divided by 0.9 equals 0.11. And finally, for this one, we would have 0.8 moles over 0.2 molarity. So this last K is equal to 4, verifying that it is the largest one. Okay, one more practice problem. For our first reaction here, H2 plus I2 to 2HI at 298 K, our Kp is 794, pretty big. And at a different temperature, at 700 K, the same reaction has a Kp of 55. So we're asked, is the formation of the product favored at the higher or lower temperature? Well, we know that if our K is much greater than 1, that means that we have a lot more of our product than we do of our reactants. In this case, they're both greater than 1, but the constant is much greater at the lower temperature, at 298 K, meaning at the lower temperature, at 298, K equals 794. So at the lower temperature, we have a higher K, meaning that then we would have more products. So at the lower temperature here, with the higher K, we have much more HI. What is that? We would have less HI here with a lower K at the higher temperature. So the answer would be lower temperature.